Good evening. This is lecture number 3. The first part, we're starting on section 4.3, which is Gauss-Jordan elimination. I'm going to do some preliminaries before we get talk more about Gauss-Jordan elimination. So our goals for today are to recall and easily convert a system of linear equations to an augmented matrix, and then some new things to recognize reduced form matrices and determine the system solution from a reduced form matrix. And then we should be able to recall, state, and apply the allowable elementary row operations, and then understand and apply Gauss-Jordan elimination. That's kind of the big goal for today, is the Gauss-Jordan elimination. So let's get to it. Gauss-Jordan elimination is an algorithm. It's a method, a way of doing something to get any matrix into a reduced form. This method applies to matrices of any size or dimension. It can be used with augmented matrices, which is what we've done so far, what we've seen so far. But you can also use it with an augmented matrix to find the inverse, which we'll see a little bit later in section 4.5. Typically, we're not going to do it to solve systems that are larger than 3, often the 3 by 3 matrix, etc. We should recall how to convert a system of linear equations to an augmented matrix. Now, we're going to talk a little bit about reduced form. Reduced form is kind of our goal and objective. So, reduced form. Reduced form is when every row containing all 0 elements in it is below every row containing at least one non-zero element. 2. The leftmost non-zero element of each row, what we call the pivot point, is a 1. 3. All other elements within each pivot point column is a 0. And the pivot points follow a diagonal pattern. They're not necessarily on the diagonal. They follow a diagonal pattern. This is a little bit hard to say with these 4 points, but you'll come to recognize them pretty quickly and easily. We're just going to look at some examples of them, and that'll probably help clear it up. So this first set, these are proper reduced form. Diagonal, so stepping through, let's see, every row containing all non-zero elements. Well, this doesn't have any. But we have a pivot point, which is a 1. Everything else in this column is a 0. Then we move down to the next pivot point, a 1, and everything else in the column is a 0. So this is proper reduced form. And then there's a diagonal pattern. A pivot point in the upper left, we're always starting with the upper left for our pivot points. And upper left is a 1. Everything else in that column is a 0. The next one, we look for another pivot point, and all we end up with are zeros. So now we take a look at every row containing non-zero elements is zeros, which is what we have here. Okay, and when we talk about non-zero elements, we're generally speaking just about the square part of it. So we're talking about the squared part of it. So we're talking about this part of it right here. Okay. Now, next example, we have a 1 in the pivot point. Everything else in the column is a 0. We already kind of indicated that this is going to be a all 0 elements version, and it is indeed all 0 elements. It's below every row containing at least one non-zero element. The next one, again, 1 in the farmost pivot point, zeros. Move down, a 1, every other column is zeros. Move down to the next row, a 1, everything else is zeros. So this is proper. Taking a look at this one. We have a 1 in the first pivot point. Everything else in that column is 0. So we move down to the next. We have a 1 in the pivot point. Everything else in that column is zeros. Now we're looking for another pivot point. You don't see another pivot point, but we do know that every row containing all zero elements is below every row containing at least one non-zero element. We have a 7 and a 2. That's okay in this case because we're following the proper pivots along the diagonal. We just ran out of pivots. I'm going to turn this off as I'm probably going to do some in a little bit. There we go. And then finally, our last example, a 1, a 3, a 7. Our first pivot point is a 1. Everything else is zeros. We check. We have no more pivots. However, we have zeros. A row of zeros and a row of zeros. These are all okay. We're going to take a look at some examples that are not reduced form. Not reduced form, and then I'm going to say why they're not reduced form. This is not reduced form. It has a 5. This needs to be a 1. This is not reduced form. It has an M. This needs to be a 0. Not reduced form because this needs to be a positive 1, not a negative. Not reduced form. Not all zeros in these columns. Not reduced form. Not a 0. Not reduced form because this row, the non-zero rows, are not below all rows containing, the 0 rows are not below all rows containing non-zero items. So this last row, 1, 3, 7, should be the first point. This does not follow, pivots also don't follow a diagonal pattern. Recall row operations. The row operations that are allowed, and this is just a review, and we're going to need this, and then I'm going to break, and then we'll go into and create a different part 2 of the lecture. And that'll be a little bit longer. That'll be a longer section. So recall that there are 3 row operations that are allowed. When you do these row operations, you end up with what are called row equivalent matrices. And we use these row operations to find a row equivalent reduced form matrix. We now know what the reduced form looks like. And so we know what the row operations are. Interchange any 2 rows, multiply any row by a non-zero constant, and add a constant multiple of one row to another. And that will end part 1.